Welcome back to Stream 3. My name is Kristina Kadar. We will continue with tasks about trustworthy machine learning. We have 3 more speakers in this session. We start the session with our invited speaker, Krishna Gummadi. He is scientific director and head of the networked systems research group at the Max Planck Institute for Software Systems. The talk is called Quantifying and Mitigating Algorithmic Discrimination. Professor Gummadi will discuss some fundamental questions about algorithmic discrimination. For example, how do algorithms learn to make discriminatory decisions? Professor Gummadi, up to you.
Thank you. Thanks, everyone. Thanks for inviting me to give this talk. I'm going to talk about a topic that has engaged me over the last several years, which is about quantifying and mitigating algorithmic discrimination. So let me start off by setting the context. I'm broadly interested in algorithmic decision making, and by this I'm referring to data-driven decision making, where the process of how to make the decision is learned using data from past decision outcomes. Now, this sort of decision making by algorithms is increasingly influencing every aspect of our lives. For instance, if you think about the search recommender or reputation algorithms on online sites like Google, Facebook, Twitter, YouTube, and so on, you have increasingly algorithms moderating our social discourse, determining what sort of news people get to see, who people get to meet, and what sort of services are offered at what prices. And then you have match and market making algorithms that are increasingly used to match producers of goods and services and information to consumers of goods, services, and information. So for instance, on gig economy platforms like Uber or Airbnb or startups like Kickstarter, you have essentially algorithms matching riders to drivers, travelers to hosts, and entrepreneurs to venture capitalists. And finally, you have risk prediction algorithms that are increasingly being used by police departments around the world to determine where to send the police, or based on predictions of in which neighborhood the next crime is likely to occur. You have algorithms being used in child welfare to determine which children are likely to injure themselves, or which of your employees are likely to leave your company, and who should be given loans and who should be denied loans. Now, clearly, given all the life-affecting scenarios in which algorithms are being used, recently there have been a number of concerns about their fairness. And these fairness concerns are quite broad. For instance, there are concerns about discrimination in predictive risk analytics. I'm going to focus mostly on this, or pretty much most of the talk on this particular topic. But here I'm showing an article titled Machine Bias. And the article says that there is a software used across the country, and the country is the US, to predict future criminals, and that it is biased against blacks. Another sort of fairness concerns arise out of opacity, or the lack of transparency of what data about users is being gathered, and how the data is being used to make decisions that in turn affect the subjects of the decision making. So there are some very interesting books with the titles like The Black Box Society and Weapons of Math Destruction that highlight the problems with such decision making. And finally, there are a number of scenarios where there are implicit biases in search and recommender systems. So here I'm showing an article that appeared in New York Times that was talking about how when in times of crisis, when people go to read or hear news on YouTube recommender systems in certain situations ends up diverting people towards the far extreme opinions. Now, in this talk, given that it's only 15 minutes, I'm going to focus very narrowly on discrimination. Now, I want to emphasize that discrimination is a very specific type of unfairness, and it doesn't cover all types of fairness. It has been well studied in social sciences, political science, moral philosophy, economics, and law for over 100 years. And a majority of countries today have anti-discrimination laws, and it has also been recognized in international human rights laws. And what I'm going to argue today is that it has been studied less from a computational perspective, and that there is a need to study it from a computational perspective, especially when in the context of algorithmic decision making. Now, this naturally poses the question, what is a computational perspective and why is it needed? To understand this, let's start with the definition of discrimination. And I'm going to start with a somewhat normative or a moralized definition. So this is a definition that I picked from the Stanford Encyclopedia of Philosophy. So what it says is discrimination is about wrongfully imposing a relative disadvantage on persons based on their membership in some salient social group. Now, hopefully most of you would intuitively agree with this definition. But the challenge comes from operationalizing the definition. Now, what do I mean by operationalization? What I mean is, how do we make this definition clearly distinguishable, measurable, and understandable in terms of empirical observations, which is what you would have to do in the context of algorithmic decision making. Now, this challenge boils down to operationalizing 4 fuzzy notions or fuzzy words that I used in the previous definition. The first is, what constitutes a relative disadvantage? What constitutes a wrongful imposition? What constitutes based on? What constitutes a salient social group? These are all English words, and you have to have a precise, we have to have a way of formalizing them if we plan to ensure that an algorithmic decision making is non-discriminatory. Now, rather than go through each one of them and how we formalize them, what I'm going to do, given the limited time, is I'm going to illustrate how to do this in the context of a specific case study. And the tool that I'm going to focus on is a recidivism risk prediction tool called COMPAS. And it is built by a commercial company called Northpoint in the US. Now, what COMPAS does is it estimates the likelihood of recidivism. Now, recidivism is the phenomena of criminals reoffending in the future. Now, COMPAS does these predictions based on the answers that defendants give to a very long questionnaire. These are the input features that it uses. And the output of COMPAS is essentially the risk of somebody reoffending. And these risk assessment scores are used by judges and parole officers in making their decisions across multiple US jurisdictions. Now, COMPAS has been trained over big historical recidivism data. So it's been trained over big data of past records of who has been left out on parole and who has recidivated. And the designers of COMPAS were actually quite careful to ensure that they did not use sensitive features like race when they're training this particular data. And the reason for this is actually the designers were quite aware of the potential for non-discrimination. And in fact, the designers' goal was to reform the criminal justice system in the US, which several studies have shown has been driven by racial biases when you have humans making the judgments. In fact, the big idea of the COMPAS designers was that rather than rely on subjective human decision makers, if only we can nudge them with objective algorithmic predictions, you would end up having a much better and fairer decision systems. Now, the assumption is that algorithms have no pre-existing biases. This is one of the assumptions that they made. And the other assumption is that algorithms simply process information in a very consistent manner. Now, what they mean by that is if you give a certain set of inputs, you would get the same outputs no matter what time you query an algorithm, unlike judges who are known to give much more meaner sentences when they're hungry before lunches, as opposed to when their stomachs are full after lunch. So the hope was that we could make accurate predictions without using race information. And this way, we could ensure that if there is a black defendant and a white defendant with the exact same features, they would get exactly the same outcomes. And this, the designers thought, would lead to parity in treatment. That is, there would not be any disparity or inequality in treatment, and therefore the algorithmic decision-making would be non-discriminatory. Now, this proved to be a pretty compelling argument, and as a result, the system was reasonably widely deployed. And 2 years after that, ProPublica, an investigative journalism organization, wanted to check if the COMPAS tool's estimates were really non-discriminatory. Now, to do this, what they did was they got data about defendants, both black defendants and white defendants, in a county in Florida called Broward County. And then they created a confusion table, confusion matrix, as I'm showing here. So the first row, the top row of the confusion matrix is about is data for defendants who actually stayed, who actually recidivated. And the second row is the data for defendants who actually stayed clean. The columns are showing the risk prediction that were given by COMPAS. The numbers in green are the correct estimates, and the numbers in red are the wrong estimates. Now, from this confusion matrix, they computed two simple measures, false positive rate and false negative rate. Now, when ProPublica computed this, what they found was that both false positive rates and false negative rates are considerably worse for blacks than they are for whites. The false positive rates for blacks is twice as that of whites. The false negative rate is half of that of the whites. Now, keep in mind that higher false positive rate is bad and lower false negative rate is bad. So along both dimensions, the error rates are much worse for blacks than for whites. And this is what they recognized as disparity or inequality in mistreatment or error rates. And this is what is behind that article called machine bias. Now, when this article came out, there was a lot of discussion and debates, both within the academic communities and more broadly. And there were a number of questions that were being raised. And a couple of questions that the academic machine learning community started asking are, why does the COMPAS tool show high racial false positive rate and false negative rate disparity despite being trained without the race information? How did the algorithm end up learning this sort of a bias? And the second thing is, could the COMPAS designers have trained the COMPAS in a different way to lower the inequality in the error rates? Now, I'm going to try to quickly answer these two questions. So first, why does the COMPAS classifier show this high disparity, despite removing or stripping out the race information from the training data? Now, to understand this, let's look at how COMPAS learns who recidivates. It just simply trains over data about past outcomes. So it has a table of information about various different defendants, their features, and who recidivated and who did not recidivate in the past. And what COMPAS was doing was to learn a decision function, a statistical decision function over the features that separates the two classes of the people who recidivated from the people who did not. So here I'm showing the same data in somewhat geometrically illustrating. So you have a bunch of features, and then the ticks are the people who stayed clean, and the crosses are the people who actually recidivated. And the goal of COMPAS is to find an optimal, that is the most accurate decision boundary that separates the ticks from the crosses. And what I'm showing here is the most optimal linear or a straight line boundary, but all the observations that I'm making would apply even for nonlinear boundaries. So what COMPAS is trying to find is, of the millions or infinite number of straight lines that you can draw on the plane, what is a straight line that does the best job of separating the ticks from the crosses? Now, how does COMPAS find it? Well, it was using traditional machine learning models where you typically define and optimize for a loss or a loss function. So these loss functions typically capture the inaccuracies in individual predictions. And what you try to do is minimize the errors across all examples in the training data. Now, typically, you try to choose functions that allow for efficient optimization. Like typically, people in the machine learning community end up using some sort of convex optimization, convex functions often. Now, taking a look back at how COMPAS computed the most accurate linear boundary, let's say it computed using the least squared error, minimizing the least squared or minimizing the squared errors. Now, notice that the linear boundary seems to do a pretty good job. But now let me reveal the group information or the groups that these points belong to. So let's say the points now belong to two different groups, two different races, say the orange race and the blue race. Now, all of a sudden, notice how the boundary that is most accurate for across the entire population is making far fewer errors for yellow than they're making for the blue race. Worse, the types of errors are also quite different. For one, it is a false positive errors, and for the others, it's false negative errors. Now, in some sense, if you think about this shouldn't be surprising, because we asked the algorithm to pick a boundary that is optimal for the entire population, but this can well lead to a boundary that is suboptimal or optimal to different extents for the different subgroups of the population. And that explains why you have inequality in error rates. Now, notice that this inequality has got nothing to do with bias in the training data, either the sampling biases or the labeling biases in the training data. This can happen in any system, and this is a point that is worth emphasizing, because oftentimes biases in the learned decisions come from biases in the data. But even if the data was unbiased, because of the objective functions, the outcomes could be biased. Now, how do we train non-discriminatory classifiers? Suppose if we wanted to fix this, how would we do it? Now, to avoid discrimination, what we need to do is to specify the discrimination measures as constraints on the learning process and optimize for accuracy under those constraints. Now, what I mean by this is typically whenever you're training your algorithm, you're trying to minimize the overall error rate across all the population. Now, we try to minimize the overall error rate subject to the constraint that the error rates for the black race is the same as the error rates for the white race. Now, this is the new problem that we should be solving. Now, notice that in the process, what we're doing with these constraints is we're embedding ethics or values when learning. Now, there is no free lunch. Anytime you add a constraint, you're going to give up something on the primary objective function. So this inequality, when you try to reduce the inequality in error rates, you would be lowering the overall accuracy. And another important point is that to actually solve this optimization problem, you need race information in the training data. So while the intent of removing race information from the training data was quite good, actually not having the data would make it impossible to solve this sort of a constrained optimization problem. So, of course, the technical challenge is how do we learn efficiently under these constraints? And this is the technical challenge that we solved in our 2017 paper. But I'm not going to go into it. And instead, let me just show some high-level results on whether these constraints actually work in practice. So to test this, what we did was we used the ProPublica data set from the Broward County in Florida that I showed you before. And then on the data set, we trained traditional classifiers without the constraints. These are the traditional black box machine learning models. And then we achieved an accuracy of 67%, but there was significant inequality in both false positive and false negative rates. Then we trained the classifiers using our fairness constraints. We were able to significantly reduce the disparity in the error rates. As you can see, it reduced from 20 to 3 and 30 to 11. However, we weren't able to move it all the way down to 0 because it's an impossibly hard task in this data.
Professor Gummadi, I'm sorry to interrupt. We have 2 minutes left in total, just to let you know that we will need to wrap up and maybe have questions.
Actually, I'm done at this point.
Okay. Sorry to interrupt you. I mean, if you have a final slide, please feel free to show it still.
So, all that I wanted to say was maybe I can end with this slide, which is the highest level insight is that when you're learning, when you're trying to do ethical learning, we have to remember that the way in which we set up the learning objectives implicitly embody ethics, and that most traditional machine learning models effectively end up reflecting utilitarian ethics, whereas there are lots of scenarios where we might want to go for something beyond utilitarian ethics. That's it.
Well, thank you very much for first insights into this really important and relevant topic, I think. It was a short talk, I know. We have one question from the audience. How could this output be analyzed to train algorithms according to fairness? So can you imagine having some kind of ranking? For example, Facebook's recommendation algorithm is 5% more fair than Google's recommendation algorithm. Can you imagine something like this to be used in
Yes. So this is a very, very active area of research. But the tricky point always is what would be a measure of unfairness that would be acceptable to the society. So once you have such a measure of unfairness, then we could essentially rank different types of algorithms. But the tricky or the most contentious issues often rely around operationalizing or finding a right measure to quantify the unfairness.
Okay. Thank you very much for joining us today, and I hope to see you again at the Swiss Data Science Conference.
Sounds good. Thank you as well.
Bye-bye.
Bye.